Hello and welcome to the second and last session of our Enduro India CAE workshop here at SimScale. My name is Milad, and today we will continue our journey through the world of computer-aided engineering and talk about computational fluid dynamics and how you can leverage the free online simulation platform SimScale for your Enduro India or Badger SAE design. Today with me is my colleague Krishna, who has prepared a very nice live demonstration. But first of all, let's take a look at our today's agenda. And as I mentioned, today we're going to talk about CFD, so that's why we will have an introduction where we will talk about the most fundamental aspects of CFD, including the governing equations and also some hands-on modeling knowledge you should really know in order to be able to create accurate simulations. This will be followed by a live demonstration of Krishna, where he will show you how to prepare a CFD analysis for scavenging in the Excel manifold of the Badger SAE car engine. We have also prepared a homework assignment for you, which will be presented afterwards. And finally, if there are any questions, we are happy to answer them. Yes, since some people joined today for the first time, I would just like to talk about some quick facts before we start our journey. First of all, the idea of this workshop, to put in a nutshell, is to enable students participating in Enduro Student India or Badger E to leverage CFD and FEA simulation for their car design. And during this workshop, you will learn everything you need to know to get started successfully on your own. And this workshop comes with optional homework assignments, and you can qualify for a certification by submitting these homework assignments. We will record all this session and later on send the recording to all registrants. And another great opportunity is that SimScale is actually going to sponsor every Enduro Student India team which wants to use simulation. And our sponsoring includes the possibility to create private projects, so professional plan of SimScale, as well as free access to our learning resources, including online trainings, documents, as well as dedicated support. We really help you to get started and to implement and adapt simulation to your design process. And last but not least, we will have a lot of great and exclusive events and trainings for teams sponsored by us. There are only 3 requirements. The first requirement to get this kind of sponsoring is that you're an enrolled student and a member of an official Enduro Student India team, and you have, or at least one person of your team has to submit all 2 homework assignments. And the deadline for the first homework assignment basically ends today at 12 p.m., but we decided to extend the deadline for some days. So you still have all the chances to submit the homework and get sponsored by us. Right, now let's talk about some fundamentals of CFD. And those of you who joined last week already know what FEA is based on. And basically, CFD is quite similar to FEA. And there is some confusion always because of the name. So CFD stands for Computational Fluid Dynamic, which clearly refers to simulation technology, a simulation tool which can model the behavior of fluids. And most of the CFD codes are based on FEM, the finite volume method. We will talk about the meaning of the name later. What I want to say, sometimes people use FEA as a synonym for structural analysis, which is basically fine. But don't get confused because of the different terms. And basically, the only thing you have to remember that CFD stands for fluid simulations. And the reason why CFD is most of the time based on the so-called finite volume method should be clear if you take a look at the slide. So the history of CFD is very interesting. Basically, 200 years ago, several scientists independently discovered different equations, which are today called the Navier-Stokes equation. And the Navier-Stokes equation are a set of partial differential equations which describes the conservation of mass, momentum, and energy in a fluid flow. And basically, if you think about the result of a CFD simulation, what do I need? Basically, a CFD simulation consists at least of a velocity vector and a pressure scalar field. So we have u, v, and w, which are the components of velocity in x, y, and z direction. And these three velocity components, they are depending from x, y, z, and t. Just imagine you have a velocity component for every point in x, y, and z direction for every time step. And basically the same with pressure. So this is what we want to have if we are running a simulation. The problem is that this Navier-Stokes equation I talked about, you cannot solve them analytically. So if you, in some simple cases, like pipe flows or 1- or 2-dimensional flows, it's possible to find an analytic solution which will give you back these functions. But in most of the cases, it's not possible, especially everywhere where we're talking about real-world geometries. We cannot solve them analytically, so what can we do? And we are very happy because actually like 150 years ago, people start to think about numerical schemes and algorithms. And we can't solve the Navier-Stokes equation analytically, but numerically, and that is the general purpose of CFD. And just as an example, for example, we have the conservation of mass. And the conservation of mass basically says that the rate of change of mass is equivalent to the inlet mass flux minus the outgoing mass flux. And basically it's the same for momentum and energy. And instead of solving this equation for a continuous fluid domain, which we cannot do, we will divide the model into small elements, which we can describe, for example, hexaedral, tetrahedral elements, and apply this conservation laws on this volumes. And that's the point. In FEA, we talked about elements, and here we're talking about cells of volumes. And this is a finite volume model. And there are also other approaches for CFD, but finite volume is, I would say, the most popular. And basically now we can really talk about the general process at all. So the first step is that we divide our domain into a finite number of volumes. And this is basically the discretization of our domain. The only difference is at FEA, basically, we got values for every node of the elements. Here we get only a value for the center of the cell, which means if this is our mesh, we will only know the pressure and the velocity for the center of the cells. And between the centers of the cells, we have to interpolate. However, so for example, if we have a wing, aircraft wing, this is how a mesh can look like. And now, this is a very important part, what we're basically doing is that we have this continuous partial differential equation. We cannot solve it. And first of all, we're making it from a continuous, bringing it from a continuous to a discrete problem by meshing it, by dividing the fluid domain. But this is still not simplified enough to solve it. And the next thing is applying a very fundamental theorem of mass, the divergence theorem, or also called the Gauss theorem. And basically, if you take a look at the equation, it says the volume integral of the divergence of the field F is equal to the surface integral of the field over the surface. And basically, this relation gives us a direct relation, or this equation gives us a direct relation and allows us to calculate what is happening inside the cell, inside the volume, just by taking a look what is happening on the boundary surface. And applying this divergence theorem on our device domain, on our mesh, will convert this partial differential equations to a linear equation system. And basically, that's the trick. And now we can solve this linear equation system. And what will happen, and that's another very important point of CFD, is that we cannot solve this linear equation system directly. We can only solve it numerically. So we cannot apply, for example, some methods we know, like decomposition methods. And now, and that's a very important point, basically what we do is that we need the solution in the end is a very, very, very large vector or set of large vectors. And we need an initial solution to calculate the actual solution. What I want to say is that the equation we have, the equation system, only allows us to calculate the error of our solution compared to the analytic solution, but not the value, only the error, and to calculate based on this a better estimation as the next step. And this iterative approach is very important in CFD. And I hope that this animation will illustrate to you what this exactly means. Now, this animation, you can see the velocity field and the pressure coefficient field of the fluid flow simulation around the motor eye. And you can also see that the time is changing. And this is actually not physical time, it's pseudo time. It's basically the number of iterations. So I created a snapshot of the field starting from the initial solution and every following iteration. And what you can see is that, and just wait until we start again from 0. At the beginning, the field is completely unphysical. The results are really bad. And after some time, you can see like how the right solution is developing and how it's converging the whole field towards the right physical solution. And now I would like to talk with you about convergence. And that's a very important aspect of CFD. And like most of numerical methods, in CFD we have an iterative approach, which means we're starting with a rough solution, and we will iterate it until it becomes more accurate and accurate. And this also means that you have to be careful, because CFD can also mean colorful desktop, nothing more or less than a bright picture. And to make sure that your results are physical and accurate, there are some things you should consider in some, let's say, checks. And one important aspect is convergence, which means that we want our actual result to converge during the process to a very accurate one. And the first aspect is the so-called convergence of residuals. And residuals are basically the error of our solution, and in this case, the average error of our solution. And that's another very fascinating aspect of this Navier-Stokes equation. We cannot solve it analytically, but we can calculate the error of the solution quite easily, because we can just apply the three principles of conservation for mass, momentum, and energy, and just calculate like what is missing or too much. And here you can see a plot of this average error for the different quantities. And usually it should become smaller and converge towards a fixed value, which should be at least below 10 E minus 3. And sometimes you can see jumps like this, mainly if you do a steady simulation of a turbulent flow, which is related to the turbulence modeling most of the times. And however, at the end of the simulation, your residuals should be low, stable, and that's very important. The next thing are forces and integrals of patches. So, I mean, this residual convergence, just say that your problem is converged numerically, but just imagine you use the wrong equation, or then it can still converge, but the results are, let's say, wrong. So another good thing you can do is like calculating the force coefficients or forces for a patch or some other variable you can integrate over the patches, and then look how they develop. And here's how it should look like. And you can see at the beginning, even the direction of the resulting force is changing, and then after some time it becomes stable. And finally, another very good convergence check can be done by probes, for example, taking a look at the pressure at the critical point of the field over the iterations. Finally, I would like to talk about two important aspects of CFD. The first one is wall modeling, and whoever of you have worked with CFD, I'm quite sure you have heard about it. And let's start like this. Just imagine we have this plate here, this flat plate, and we have a flow over this flat plate. As you know, the air at the top of the surface of the plate is interacting with the surface, and there is friction. And what will happen is you take a look at the velocity profile represented here by these vectors, that we have like free stream velocity u0, and if you go lower to the wall, you get this profile, this curved velocity profile. And if you take a look at the velocity profile downstream, you will see that the profile has changed and become less sharper and a little bit thinner here. And that also these distances have increased until you again reach, let's say, the free stream velocity. It go up here, it was here, and now it's here. So what can we say about this flow? The velocity in y direction, in this direction, is very, very small compared to x direction. And the velocity changes slowly in x direction, which means if you take a look, and the change here is quite small over this distance, which is a very long distance. But in y direction, it changes very rapidly. And this kind of problem for characteristic is called boundary layer. And this boundary layer has a thickness, which is defined by a criterion. For example, mostly used is the criteria that 99, everywhere where the flow is below 99% of the free stream flow, this is part of the boundary layer. And this boundary layer has a massive influence on the overall flow structure. For example, here we have this flow around the sphere, and the only say we are changing is the Reynolds number. So basically, we're just changing the inlet velocity. And here you can see, like for low velocity, we get laminar for nose operation. If we increase it further to 10, we get some steady separations. And if the Reynolds number is even higher than 100, we have unsteady vertex shading. And what I want to show you with this graph is that if you also look at the drag coefficient, it's dropping. And this is a very good example how the boundary layer can like affect the overall flow. And this is not all related to the boundary layer, but what I wanted to say is that modeling the boundary layer is essential for getting a good result if you want to simulate turbulent flow. And therefore, we have to talk about how to model it there. And before I talk about exactly how to model it, just the final aspect about wall modeling and forces on patches and bodies. Most of you know that we have drag and lift force in aerodynamics when we talk, for example, about external aerodynamics. But basically, these forces have two components, and that's something a lot of people don't know. Most of people think it's only related to the pressure, but that's not true. The surrounding fluid exerts pressure forces as well as viscous forces on an object like a wing. And the pressure forces are related to the pressure difference between upper and lower side of the wing. And if you integrate right now the pressure distribution over the surface, or using the surface normal, calculating the product from surface normal and pressure scalar will give you the pressure force, which has a component, lift and contract component. For the viscous component is based on the wall shear stress, and there you have calculated a little bit different. And the overall forces are a combination of both pressure forces and viscous forces. And it's very important to understand that in order to model the viscous forces correctly, you need to have the right boundary layer modeling. And there's also interaction. If this is modeled wrong, you will also get different pressure field because the flow separation, for example, changed. But in the end of the day, it's important to model both of them correctly. And the viscous forces can be modeled by using layer elements, which we'll talk about right now. And for the pressure forces, it's all about region refinement, mainly around the wing. Okay, now let's make it clear what's wall modeling. Here you can see image photography of flow separation at the leading edge of a wing, and here you have some recirculation, some turbulence. And if you take a look at the boundary layer, as I mentioned, we have this velocity profiles with a high change in y and a slow change in x direction. And basically, our problem is if we would use here for resolving this gradient, if we would use uniform cells, we would waste a lot of elements because we need the accuracy in y direction, but we don't need a high accuracy in x direction. So what we do, we introduce flat cells called boundary layer elements or prism layer elements. And these flat cells resolve directional changes of velocity. They are very sensitive in the normal direction where we have the high change of the boundary layer. And they are really necessary for realistic simulation of turbulent flow, as I mentioned. The only thing you should never do is applying these on physical patches, non-physical patches like inlets and outlets. I will tell you why. Let's just imagine this will be an inlet phase. Then we have low change in y direction, but not a high change in x direction. So they will need uniform cells. And it's not only important to use this layer, but it's very important that the first layer has the right height, so that the distance between this cell and the patch has a defined plane. And this is based on several factors. But however, like 150 years ago, I think, there were the first investigations, and people find out that there is something like a general velocity profile for turbulent flows. And if you take a look at this law, which is called the law of wall, you will see that there is a direct relation between dimensionless velocity and dimensionless wall distance. So what means dimensionless? Dimensionless means that we don't take the absolute values of velocity and wall distance, but that we calculate something like a relative dimensionless value. Dimensionless means that it has no unit. For example, the dimensional length of a wing is the actual or the dimensional chord length of a wing. It can be calculated by dividing the wing position by the wing length. It's just about making things comparable. And if we take a look at the boundary layer, and here on the x-axis you can see the distance normal from the wall, and on the y-axis you can see the dimensionless velocity. And then we can see that there are three areas. There's first of all a viscous sublayer, and in this viscous sublayer you can basically say u plus is equal to y plus. So it's a linear relationship. Then we have a buffer layer and a log region inner layer. And the buffer layer and the log region inner layer, they are calculated mainly using the turbulence model. Krishna, during this demo, Krishna will also set up the turbulence model, and then I think he can also explain a little bit why he's using the model. But this viscous sublayer, this can be represented by one cell, and that's the idea of using wall functions. To put it in a nutshell, if I want to make sure that I model my boundary layer flow correctly, I need to resolve the high gradients in y direction, and therefore I need a very fine mesh in y direction using the layer elements. There are two options. One option is to directly resolve the full wall model, the full wall velocity profile. Then I need to have a wall distance y plus value of 1, which will lead to very flat cells and a high number of cells in total. The other one is that I can put this whole region, instead of resolving it, into one cell, which saves a lot of computational effort and is more practicable. And there I need to make sure that I have, for example, for some turbulence model, a y plus between 30 and 300 for the first cell. Otherwise, the results will be wrong, because this whole area of the cell will then be treated as a viscous sublayer. Okay, finally, this aspect I want to talk about general CAD problems. Because especially when it comes to CFD, you have sometimes more complex surface models, and you have to prepare the model in order to be able to create a simulation. And one reason is that, first of all, CAD models which are designed for production are not suitable necessarily for the simulation, and also that importing CAD, so the imported CAD models have too many details. And another big problem is that during the import, a lot of problems can happen, translation errors, and then you have errors in your model. And the most common errors is that the volume is not closed, which is a big deal for CFD, because if your volume is not closed, it's not water, not fluid tight. Surface discontinuity, so something is not connected, or if surfaces intersect each other. And this can look like this. So here on the left side, we can see an example for an intersection, and in addition, a one-dimensional face, which is not working. It has no thickness. We have the same for open volume and discontinuity here. And here I just have prepared some images showing on the left side the construction model, on the right side the CFD model, how you can prepare such a model. So here you can see all the screws were removed. Here, all the screws, which are unnecessary details. Here, everything was simplified. The same here. The spring was replaced by a body, by a bluff body, a cylinder, and here the connections were removed. The radiator, for example, was replaced by such a body and will be represented by a porous zone, which is more efficient than resolving all the small parts of the radiator. And here you can see some other major simplifications. Okay, great. Thank you very much for your interest and your time. And now Krishna will show you how to deep this knowledge with creating our own simulation of engine exhaust manifold. Krishna, can you hear me?
I can hear you. Can you see my screen?
Perfect.
Or could you make me presenter?
Not now, but I will just make you to the presenter. 1 second.
So, all right, guys, my name is Krishna, and thanks a lot for being here today. I'm going to show you the live demonstration today for an exhaust manifold. And the aim of our simulation today is going to be to explain the scavenging process in an exhaust manifold. So what is scavenging basically? Scavenging is the process through which the exhaust gases or the exhaust flow of the engine is directed out into the atmosphere. So as an engineer, you would try to think, how would you design a system like this? The main aim to design a system like this would be to have a very smooth process through which the flow can be directed out of the engine. And for that purpose, you would have to design your engine exhaust manifold in such a way that there are no blockages or there are no recirculation zones inside the exhaust manifold. And basically what these recirculation zones or blockages do is that they reduce the performance of the manifold and in turn the performance of the engine itself. So this can be analyzed during CFD, and you can use a CFD simulation for in the design process, and you can implement a CFD simulation in the design process in this method, in this way. So just the basic overview of the CFD process we'll be following. So the first step would of course be to make some hand calculations from which we can determine a starting point. And after the hand calculations, we move on to the pre-processing, where we generate the mesh. We import the CAD model first, then generate the mesh. And once we have a good mesh, we move on to the simulation part, where we set up the simulation, and it would be an incompressible flow simulation with turbulence modeling. And then we move on finally to the post-processing, and also the post-processor is included on the SimScale platform. So the entire CFD process is, or the entire workflow is implemented on the platform. So you do not need an additional preprocessor for the same. As engine specs similar to these. So the displacement is around 305 cc, and that would be around 18.61 CID. So CID is just basically a different kind of unit for the engine displacement. And it also has a set RPM. So once we know these two parameters, we can calculate the intake flow. And from the intake flow, we can calculate the exhaust flow. And this is how we calculated our exhaust flow to be around 0.04 kilograms per second. And this is now our first starting point. This is how much air we want to exhaust from our exhaust pipes. So just the basic physics overview. We have two ports. So basically the two ports are coming from the engine. And what these two, and this is basically the exhaust manifold that is made out of steel. And we have the outlet into the atmosphere. So just a basic overview, we have the two inlets at the two ports. This one would be inlet 1 and this is inlet 2. And those would be velocity inlets, and we would specify the mass flow rate on those inlets. And the outlet would be at atmospheric pressure or zero relative pressure to the atmosphere, because it is an incompressible flow simulation. We do not need to define a real atmospheric pressure. We just work with the differential pressure. And the pipe would be, of course, a wall and no slip wall, because that is how a solid body would actually behave in real physics. Because of this no slip condition, there would be a development of the boundary layer, which I'll talk about later, and also a bit Milad explained earlier. I would just go into some more detail about it. So let's just move on to the pre-processing onto the platform. All right. So here we have our geometry. These are the two inlets. This would be our outlet. And this is the entire exhaust manifold. Now we can just create a new mesh. That was the next step in our workflow. And we use a TED dominant mesh because it is a simple pipe geometry, and it would not be a very big problem if we have a TED dominant mesh with layers, and automatic would be fine in this case. And let's just set the mesh fineness to fine. And it would not be a very big mesh because the size of the geometry is not so big. So let's set the number of commuting cores to 8. And we would need a mesh refinement in our case because we want layers to grow. As Milad explained earlier, that these layers basically refine the boundary layer. And as a general best practice, there is a non-dimensional wall distance called the Y plus. And as a general best practice, you need to limit it to 1. But 1 is not so easy to achieve usually. So people usually limit it in a range of 30 to 300 and then use wall functions. So wall functions are basically adapting your solver to a higher value of Y plus. So basically that is what wall functions do. We'll talk a bit more about wall functions in the coming discussion. So let's just set up our layers. Let's call it layers. And layer inflation. And this is all I think is okay. And we need to assign it to the pipe. And just in case I'm going too fast or my explanation is not smooth enough right now, you will have a very detailed tutorial explaining the whole process to you, which will be sent to you tomorrow via email. So once we have set up all the parameters, let's just start our operation. And this would take around 10 to 20 minutes to complete. So you just look at the previously created mesh. So here we have our initial mesh. You can see that it's a pretty fine mesh for an initial simulation. And if you look at the layers, they're also pretty fine. And if you look at the first layer, it's around 1 millimeter. And this ratio between the last layer and the first layer of the mesh outside the layer should also be not too big. Otherwise, this would also cause problems in the solver. This would basically cause very high gradients in the solver, which is a really deep topic to discuss right now. But let's just say that the volume ratio between this cell and this cell should not be too high. And as we can see here, that it's a volume ratio of around 2, which is pretty fine enough. And from that perspective, we can just move on to the simulation designer. So we can just move on to the simulation designer in the workflow and create a new simulation. Let's call it sim. Let's just put this. And it would be a fluid dynamic simulation with an incompressible flow. And the turbulence model we use is K omega SST because we want to use wall functions later, and K omega SST usually performs better when we use wall functions. And let's save it. And the domain would be the mesh you just created in the previous step. And as you can see, the mesh size is around 200,000, which is not too big. It would take around 15 to 20 minutes for a simulation of this size. And the material we assign as air. So we can just import it from the material library and assign it to the fluid volume. That is basically the entire volume of the exhaust manifold. And we also need to define some initial conditions. But in our case, I think it would be not a very big issue if we leave it to the default values. They have been already set optimally for an incompressible flow. So you can leave it the way they are. Just in case you are making a very detailed simulation, you might want to calculate the initial values of K and omega, but they are usually calculated during the simulation. So it would not be a very big issue if you don't. And the first boundary condition would be our inlet. So and our inlet would be a velocity inlet, and we specify it as inlet mass flow rate as we calculated earlier. Let's call it inlet 1, and we assign it to inlet 1. The second one would be the second inlet, and then a velocity inlet with a mass flow rate of 0.02. And we assign it to inlet 2. And our next step would be to create the pressure outlet because it is at atmospheric pressure. So we just have a zero pressure, which is the differential pressure from the atmosphere. And we assign it to the outlet. And the last step in our boundary conditions would be to define the wall or the pipe itself. Let's call it pipe. And wall functions. So now here is where we define the wall functions for the pipe. So this is basically what would adapt your y plus to the solver, or it would adapt the boundary layer in such a way that it is not calling for a very, very low y plus in the order of 1, but it would adapt it or relax it in such a way that a y plus of around 30 to 300 would be also acceptable. And let's save it. And the numerics, we can just look at the numerics once, but we do not need to make any changes here because they are all adapted or optimized for an incompressible flow simulation, which is the case in our setup. And we can increase the number of computing cores to 8 in the simulation control. Let's call it 8. And a runtime of 3000, that is 50 minutes, would be more than enough for a simulation of this order. And let's save it. And we also need to set up some result control items. So basically what we want to do here is we want to monitor our averages at the inlets, the outlets, and also at the walls. So what these field calculations at the inlet do is these fields are actually converged after our simulation. So convergence is not always based on just the residual convergence, but it is also based on the field convergence on specific points of interest. So in this case, our main interest would be to have the mass flow rate and the pressure values and velocities at the inlet and the outlet to be converged, so that we can for sure say that, or we can confidently say that it's a very converged solution, and we can actually rely on this solution. So let's just set up some averages on the outlet and the inlet. So let's set up inlet average, add a surface item, and let's call it inlet 2 average. And our last average would be to average it at the outlet. So now we have all our surface control items. These we can visualize once the simulation is done in the post-processor. And we would need another calculation item which would be our y plus, because we want to also monitor our y plus, which is not automatically exported to our results. So we need to do some result control item or set up a result control item for that. And for that, we need a field calculation item. And let's just call it y plus. And this is the dimensionless wall distance. That is basically our y plus. So we have all our result control items now. We can make a quick check to just see whether our simulation has been set up correctly, whether you have made some unwanted mistakes somewhere in the workflow. But here it says that it was set up successfully. So we can just create a new run and start it. Now this run, as I said earlier, it would take around 10 to 15 minutes to complete, but you would not want to wait for that. So we just look at the previous completed run, and let's cancel this. So here we already have an initial result. So basically you can look at the flow speedups. So this is the inlet. This is inlet 1, where the flow enters from the engine and it speeds up because of this curve. As you would know that the pressure differences, or when any flow goes over a curve or a convex curve, it speeds up due to the pressure differences. So this is exactly what's happening here. You can see the red regions, which are the flow speed up. Then again, it separates here in this region. The green region is where there's a separation zone, and this is what leads to some recirculation in the pipe. And basically, this slows down the flow a bit in that region. But you can see that it does not have a very huge separation zone. So this would not hinder the performance of our pipe in such a huge manner. And we can also look at the streamlines. So basically, again, from the inlet 2, again, you can see from the second inlet, there is also these flow speed up around the curve, and there is some separation zone, but not enough to produce strong vortices, which would block the flow. There would always be very, very small vortices in the flow, which would be turbulence eddies or small scale turbulence, but that is not the aim of our simulation. We just want to see if there are major recirculation zones which would actually block the flow in a significant sense. So in this case, or for this operating point, we can say that it's a decent design. And let's just move on to our slides. So we can just now look at the convergence plots from the simulation run. So as you can see here, the convergence is 1e minus 5, so that is 10 to the power of minus 5. So that is basically the residual convergence. So that is a first step in determining that our simulation has converged. The second step would be to look at the velocities at the outlet. So these are basically the velocities at the outlet. So as you can see that all of the three velocities, the x, y, and the z velocities, have actually come to a steady state value at the outlet. So from this, we can say that our simulation has actually converged. So this is, now I'll just present a short parametric study. What we just saw in our setup or in our demo was a simulation setup for a condition where both ports of the engine would be open. So there would be equal mass flow rate from both ports of the engine. So as you can see here, we were not experiencing significant recirculation zones. You can see some small ones here in the blue regions. I'm sorry, it's the other way around. So the first port is open and the second port is closed. So again, here you can see there are significant flow speedups, small recirculation zones, but we cannot see any major recirculation. Maybe here, but that is also a very small recirculation zone. Now here, if you look at the first port open and the second port closed, here we can see that there is no flow in a whole section of the pipe. So this could give you indication that there would be strong recirculations, which would be leading to the velocity becoming zero. As you can see here, the velocity is going to zero in front of the pipes. It's just not reaching there. So we can look at the streamlines. All right, so here you can see that there are some significant recirculation zones, which you would not want in a exhaust manifold. So from this, you can say that maybe you would need some betterment in this region of the pipe or this region of the exhaust manifold. And this is how you could leverage CFD to basically design an exhaust manifold. All right. So now we come to our homework session. The homework session is basically divided into two parts. The first one would be what we just saw in our demonstration. So you would be provided with a SimScale project, which would be consisting of this geometry, which we just talked about. And the second one would be basically a parametric design of the same manifold, which would also have a dent. And this dent is now parameterized, and you could easily vary the shape of the dent, the size of the dent, and I'm sorry. Yeah. And this on-shape project would also be provided to you, and you can just change one parameter and modify the shape of the dent yourself. And once you have modified this dent, you would export it onto the SimScale platform, and you could do your own setup with the same parameters as the exhaust without the dent, and just analyze what effect does your dent have on your flow. So you also have a very detailed step-by-step tutorial, which would include the SimScale setup as well as the on-shape parametric model. So you would have a step-by-step description for the SimScale setup as well as how you would modify the model in on-shape as well. So this is basically it from my side, and I would be really happy to answer any of the questions. And back over to you, Milad, if you're still here.